Lesson 40, the Bohr model, and this is where things get really interesting for atomic models. So our last model was the Rutherford planetary model, and in that model we say that there's a very dense, massive nucleus, and then the electrons are orbiting the nucleus. That's the planetary model, but the weaknesses of that model where they couldn't explain things like why if a charged particle like an electron is accelerating, then it gives off EMR, it should lose energy and spiral into the nucleus. So Rutherford could not explain that, but along comes Niels Bohr, and he comes up with a theory to explain that. And this is where all that quantum stuff that we talked about earlier comes into play. And what Bohr suggested was that electrons could only exist at specific orbits around the nucleus. So let's just so if you have a nucleus here, then you could have an electron orbiting at this level or at this level, but you couldn't have anything in between those levels. So the electron could exist here or the electron could exist here, but not in between. And that is a concept of quantization, right? I can be a 1 or a 2 or a 3 or a 4, but it can't be a 1.5 or a 2.79. And I can only exist at these levels. Now, why could they only exist at these levels? I'm going to kind of go into into the next lesson here. We'll kind of combine all these lessons. So this is quantum theory, that things have to happen in packages of light. So here's a little package of lights. You can have that package of lights and this package of light, but you can't have half of that. The reason that we think that happens is because electrons are not. They're not. Oh, sorry. Before we continue, you should go onto YouTube and where is it? Watch this video, Quantum Mechanics, the Structure of Atoms. It basically goes over everything I'm going to say in this lesson, and this will make you appreciate it and make you understand the lesson better before you go through it. So pause the video right here, go to YouTube, watch Quantum Mechanics, the Structure of Atoms, and then come back to the video. And now I'm going to explain what the video says, and that is the reason that the electron can exist here is because the electron is not a particle orbiting the nucleus like the Earth orbits the sun. It's because the electron is actually a standing wave. The electron is a wave. So think of the electron as a wave. And if it's a wave, it has certain wavelengths. And if I draw a wavelength here, so this is the wavelength. I get a nice little pattern that works perfectly, and I get constructed interference throughout that. However, if I use that same wavelength at another distance here, I always make that very dramatic. What happens here? Oh no, that is destructive. Destructive interference. I can't spell destructive. Destructive interference. Destructive interference. So this one here had constructive interference, but this would have destructive interference. Therefore, the electron cannot exist at that radius or that orbit level away from the nucleus. It can exist here because as a wave, it creates constructive interference. And over here, in this level, it creates constructive interference. But in the levels in between, or the distances in between, it creates destructive interference, and therefore the electron cannot exist at those levels. And so now we've combined all these ideas of models of atoms and quantization and standing waves, and it's a beautiful thing to see all these ideas come together. So now let's go back now that I've given away the entire lesson and discuss it, and it says quantum mechanics, discrete energies. So you can only have this amount of energy or this amount of energy, but you can't have anything in between. It won't work that way because of the wave nature of electrons. And then we have this really interesting concept of spectroscopy. There was strong evidence of energy being released as quanta when physicists studied spectroscopy. Very hard word to pronounce. So what Bohr did here was he was looking at light sources through a diffraction grating and analyzing what colors he had seen. In these experiments, it was discovered that if a high voltage or heat is applied to a gas sample of an element in a tube at a low pressure, it will give off light. When a spectroscope is used to examine the light, it does not emit a continuous spectrum of color. Instead, each element releases an emission line spectrum. Each element gives off its own unique emission line spectrum. It acts like a fingerprint of that element. And again, if you've watched the video, then this will make sense to you. So here's what it looks like. You've got a high voltage, you've got a gas in here, in this case, hydrogen, and you put the high voltage through it, and what it does, it gives off light, and you put it through a diffraction grating, and what you see is violet, blue, green, and red at these specific wavelengths. And as you recall, E equals HF and E equals HC over lambda. So those specific wavelengths have a specific energy associated with them, and that is the energy level at which those electrons will exist. All right, getting interesting, isn't it? So that's an emission spectra. Then you have an absorption spectra. It says the opposite is also true. If we shine a continuous spectra of white light through a cool gas at a low pressure, it will absorb the light at the same frequencies as it emits. These missing lines from the continuous spectra are called absorption line spectra. So here's an example of what an absorption spectra looks like. And here are all three. So the top one is a continuous spectra. The second one is an emission. So the top one, continuous. Continuous. This is an emission spectra, and this is an absorption spectra. All right, and in the emission spectra, you've got electrons falling from a higher level to a low level, giving off that wavelength of light. In an absorption spectra, you've got electrons going from a low level to a higher level, and therefore they have to absorb energy to go from that low level to a high level, and therefore those parts of the spectra are missing because they've absorbed those frequencies of light. Then the lesson goes on to the Balmer formula, and this has actually been taken out of the physics curriculum. The reason is it's a great formula, but it only works for hydrogen, which kind of makes it useless in the long run. If that's the only element it works for, why do it? So now we just discuss energy levels. So, but before that, we'll discuss this very quickly. It says the idea of electrons existing in a specific position shows up in the n formula's n values. Because an electron would have a specific amount of energy at these particular positions, we call them energy levels. Bohr said that electrons in these energy levels are stable and do not emit EMR as they orbit. Since these electrons are not losing energy, we can also refer to these positions as stationary states. This means the electrons are stationary. This does not mean that they're stationary, just that they are in a stable position. Bohr theorized that energy in the form of EMR is emitted when an electron falls down from one level to a lower level and absorbed when it jumps up a high level. Okay, and then we're going to watch this FET for a minute or two, and then we're going to do this lesson in 2 parts because it's just a pretty intense lesson, and I want you to have time to absorb it. So where's the FET? Where is it? There it is. Here's models of the atom. I don't want to show this too long because it takes up too much memory. Here we go. Here's the billiard ball model of the atom. Right? Here is the plum pudding model of the atom. Yeah, and each time you see something being emitted, something bouncing off there, that's a photon of light being emitted. Here is the classical one. Oh, we'll watch that one again because it's great. It just doesn't last very long. The electron immediately spirals into the center and kaboom. Okay, here's the one you got to watch. This is the Bohr model. This is the one that we're presently on. And watch the electrons. There's the electron right there. There it is. And you can see it's getting hit by these photons of light. And if it gets hit by a photon with a certain amount of energy, it will knock it up to a higher level. So there's and then when it's in that level, do you see that? It got knocked down to a lower level and it emitted EMR. Okay, but there it is, and the electron can only exist at these certain levels. It can't exist in between them. Then you go to the de Broglie, which is coming up next. So we'll stop it right there for now.